Hello. Okay, before we proceed on this next video, in this particular video of MOSFET operating regions, so there was one small mistake happened from my side. Maybe you can just look at this particular problem where we actually asked to find the operating region of this, because this was the problem given, and it was asked to find what is the region of operation of this particular MOSFET, and of course this is that problem. We actually wrote this is VDS SAT, which is nothing but VGS minus VTH, which is 0.2 volts. We were actually comparing VDS with VDS SAT. VDS is given by this expression in which ID was unknown. While finding the value of ID, we substituted all these values, and by mistake this current actually came out to be 400 microampere. I don't know how does that mistake happen. Actually if you substitute all these values, the current comes out to be 160 microampere. I think most of you have noticed it. Substituting that current as 160 microampere into this equation, VDS comes out to be 1.64 volts. This is 1.64 volts, which is far more than 0.2. So the region of operation of this MOSFET still remains as saturation region. So this is one small mistake. Instead of 160 microampere, by mistake it is taken as 400 microampere. Coming to the second problem, of course in the video itself I have mentioned take VDD as 0.9 volt. If you take VDD as 0.9 volt, if you substitute this VDD as 0.4 and this VSS as 0.4, because here we are simply substituting the magnitudes of this VDD value and VSS value, because the sign of these voltage sources have been already taken care in the KVL expression. You simply substitute what is this. So this is like 0.9, you have 0.9, and this is also 0.9. The addition of these two happens to be 1.8. So ultimately all other things remains the same. So this is only thing is that instead of taking this as 1.8, I took it as 0.9. So that is the second clarification, and we'll just move on to this AEC and ME. Okay, in this problem we are asked to find does the value of RG, the question is the value of RG will not affect VGS. So the options are no, it affects, the RG value will affect VGS. The second option is yes, RG will not affect, and it may affect, and I don't know. These are the four options. Let us try to understand it. If I understand from this, this is like circuit what I have. So VGS can be written as voltage at this point with respect to ground here, because source is grounded. So voltage at this point is nothing but voltage at this point, because this is an insulator, current won't go into this MOSFET. So this current is 0 means, so this drop is also 0. So no drop comes across this RG at all. So when there is no drop happening across RG, so the value of RG does not matter for knowing the DC voltage of this VGS. So VGS is having an expression VDD minus ID into RD, where RG is not at all coming into picture. So since this is your VGS expression, and VGS is not affected by RG, but the value of RG using Miller's theorem can be split, because this is a floating component. It can be represented as RG dash on this side and RG double dash on the other side, this value of RG. So since it's at the input side, this RG dash acts like the input impedance, this acts like the effective load impedance what you can think of. So now RG value is not affecting my VGS. Of course it will certainly affect the input impedance of this amplifier. So the answer for this is RG will not affect VGS. So RG will not affect VGS. That's what the value of Rg will not affect VGS. The correct answer is yes, it won't affect. The Rg value will affect, the value of Rd will affect VGS and hence ID. So naturally, if you look at this, in this expression, VGS is related to Rd. If we change the value of Rd, naturally VGS will change. If VGS changes, if the MOSFET is in saturation region, of course it will be in saturation because drain and gate are shorted. So naturally, as VGS changes, for change in ID, naturally, change in Rd, the drain current will also change. This is the answer for that is, if I just go back here, the value of Rd will affect VGS, hence ID. The answer is true. Now, in this second question, we are asked to find the expression for VGS. So, does this VGS is given by VDD minus IDRD, VGS is 0, VGS is equal to VDD, and VGS is this. Looking at this, this is the expression what we have here. So VGS is actually the voltage at gate minus voltage source. So voltage at gate is actually it's actually connected to VDD through RG. Since no DC current flows through this RG, whatever is the voltage at one end of the RG, the same voltage is available here. So VG is equal to VDD. So what is Vs? Vs is 0, that is voltage in the source. So VGS is equal to VDD. The option is VGS is equal to VDD. The option is, the correct answer is option C. Now the value of Rg, can it be 0 ohm, 10 ohm, 100k or any value? So because you have a Rg, then what should be the value of that? So if it is not affecting my VGS, then can it be 0 ohm, can it be very large value, or can it be any value? The answer for that is, let us see. Now, one second, I have this as a, you can see now, if I write the AC small signal model of this, so this Rg, we know that DC will be AC grounded, so I am AC grounding this. This Rg will come over here, and can see this is your input voltage. You are shorting the capacitor, capacitor is shorted, and if you see this, this happens to be the input impedance. Okay, this happens to be the input impedance. This happens to be the input impedance of the amplifier. So naturally, input impedance has to be as large as possible. So Rg should be more and more to have a good amplifier characteristics. So Rg should be more. So looking at this, what we have now is, so it was, one second, it was said that now we have been given three options of Rg, whether it should be 0 ohm, 10 kilo or 100k or any value. So basically this should be large value, that is 100k. If it is 100k, it is good. Next, they are asking, does the value of Rg, should it be large because to have a large input impedance, low cost, or it reduces Ig? Of course, we already know the answer for this. The answer for this is, if Rg is more means input impedance is more. So the input impedance of this will be more and more if Rg is large, because Rg will not affect any Ig, because Ig is already 0, this Rg will not affect. So Rg more is required to have a large input impedance. So this A is the option. Next, coming to this question, we are asked to find the value of we are asked to get the expression for ID. So is ID is equal to VD minus this voltage by RD. This is true electrically to know the value of ID, but this expression will not decide the value of ID. Meaning, if you change the value of RD, ID will not change. Again, this equation is also not correct. Meaning, this RD and RS will not decide the value of ID flowing through this. This is the correct answer, because let us see what is the expression for, one second. Okay, looking at, because we were just looking at this particular thing, expression for this ID here. So we know that the drain current flowing through this is given by the expression half Kp W by VGS minus VT whole square, whereas the voltage at the gate is nothing but VD into R2 by R plus R2. The voltage at the source is ID into RS. So if you want to substitute for VGS, so VGS is nothing but VG minus VS. So I'm writing what is VGS as VTD into R2 by R plus R2 minus ID into RS. This is minus VTO. This is the expression for ID. So the option for this particular question is, it is option C. Now for a value of VG to be 0.6 volts, now can we select the value of R1, R2? It can be, of course, if you can see, if this is 1.8, then R1, R2 ratio, if it is 1K and 2K, how much is the resistance you are going to get? So if it is 1K and 2K, I'll get actually 1.2 volts. If you substitute this, then it will be 0.6. Here it will be 0.6. Here will also be 0.6. So in option B, C and D, because I know that the value of VGS is given by VDD R2 by R1 plus R2, that is 1.8 into, it is okay. Now I have the options like, okay, let me just go here, let me just take this to this. So I have these possible, one second, I have these possible, one second. Okay, welcome to, sorry, let me take out this also, let me bring this down. Now these are the possible values of now. So R2 2K, this is 3K. Now this is actually 1.2 volt. So this is not an option. In the B option, it is 1.8 into, it is 1 ohm by 3 ohm, you will get 0.6 volt. In option C, it's 1.8 into 10K by 30K. Here also will get 0.6 volt. In the D option, you have 1.8 into 100K by 300K. Here also you get 0.6 volt. In three options of B, C, D, you get 0.6 volts. So out of these three values, these three possibilities of R1, R2, which one is a preferred value? Which one is a preferred value? So how do we choose a preferred value for this? Because all the three combinations of R1, R2, which is okay, 1 ohm, 10K, 100K, for 2 ohm, 20K and 200K, for these combinations of R1, R2, R3, VGS is coming out to be 0.6 in all the three cases. Then which one is a preferred value? So now the preference comes from the fact, not while getting the not in order to get the value of VGS, but one more option I need to find. So since it's an amplifier, I am also looking at one more specification of, can I have the input impedance of this amplifier also more. So this is my Vin. If I write the small signal model of this, so it looks like this. So now this is R in, and I have this as my, okay, now I have this is my RS, and this is so and so. This is my small signal model. So this is my input impedance, where Rin is given by R1 parallel R2. So I know that I have to have a larger input impedance for a good amplifier characteristics. So this won't give me larger input impedance, this won't give me larger input impedance, this will certainly give me, among these three possibilities, a better input impedance of 66 kilo ohm. Here it will be 6.6 kilo ohm, here it will be 0.66 ohm. So out of these, now naturally this has got a better choice of resistances in terms of getting VGS of 0.6 as well as input impedance larger value. So option is 200K as R1, R2 as 100 kilo ohm. So that's what is the option. So the option here is this C. Next the question is, to have a better bandwidth of the amplifier with W by L as 50, pick the value of L and W. Again, this is a tricky question. Now W by L is, ratio is 50, W is given as 500 millimeter and length is equal to 10 millimeter, and in option B, width is 500 micron and length is 10 micron. In option C it is 50 micron and it is 1 micron. Then in option D it is 100 micron and 2 micrometer. So to have a better bandwidth, so let us, keeping that in mind, let us dwell on this. So it was asked to select which value of W by L, you just choose it for this. If you carefully notice, all the four values have a ratio of W by L is equal to 50 being satisfied. Then to have a better bandwidth, which value of which combination of width and length you select. So now we need to look into some other parameters, not just the ratio, for choosing the value of W by L. So it was given that to have a better bandwidth. So if you actually find the bandwidth equation, so we have amplifiers will usually have a frequency response something like this. So this is the deciding bandwidth, which is usually given by 1 over 2 pi R out into C out. This C out is a capacitance which is usually the capacitance which is CG DO1, which is CG DO dash, which is the Miller effect of that, which is 1 plus 1 over AV. So when you have this CG DO is actually CG DO multiplied by width. This is actually in farad. So this is farad per meter parameter, and this is the width. So I need to multiply CG DO by width of the transistor. So to have this bandwidth more and more, I know that my capacitance should be as small as possible. For capacitance to be as small as possible, my width should be as small as possible. So I have to always select a dimension of the transistor, the least one, to have a better bandwidth, because if the width is less, then capacitance is less. If the capacitance is less, F2 is more, that is bandwidth is more. To have a better bandwidth, the option among these, this is a better option. So this is a better option, provided you can able to have a length of 1 micrometer being fabricatable in your process. So among these four values, to have a better bandwidth, 50 micrometer as the width and 1 micrometer as the length, which will give me a W by L of 50, is a suitable preferred width of the transistor. Next, coming to this, now if VGS is equal to 0.8 and VTH is equal to 0.4, what is the value of RD that will give maximum output swing? Let ID be 1 milliampere. So let us try to understand what is the meaning of this output swing, RD, all this stuff. Now looking at this circuit diagram, what I have is this. So I have an input voltage. This is VDD 1.8 volt. This is RD. This is where you get your V0, and what is given is VGS is equal to 0.8 volt and VTH is equal to 0.4 volt, and ID is assumed to be 1 milliampere. Okay, we have been given the option of RD is equal to 1 kilo ohm, 700 ohm, 900 ohm and 100 ohm. So these are the possible values of RD, provided you have to have output swing should be maximum. Output swing should be maximum. So with these specifications, let us try to dwell on this. This is what I have. We are asked to find. So now let us try to understand. So this is my 0 voltage. This is 1.8. This is like 0. This is 1.8. So out of which I should keep this MOSFET always in saturation. I know that VDS sat is equal to VGS minus VTH, which is 0.4 volt. Meaning my output voltage should not enter this region of 0.4. So let me mark a point 0.4 somewhere here. So this is a region where your output is not supposed to enter. If the output enters here, then MOSFET is in linear region. So now how much is the swing that you have? So the left out swing is actually 1.4 volt. So out of this 1.4, the midpoint is 0.7 volts here. So it is 0.7. So if it is 0.7 from here, how much is this? This is actually 0.7 volt. So which comes out to be at 1.1 volt. So this is actually voltage at drain. Voltage at drain, if it is at 1.1 volt, then I can have a good swing over here. Which is maximum possible swing. So to have this at 1.1 volt, so can I write the expression for VD now? VD, that is voltage at drain, is nothing but VD minus ID into RD. So it is supposed to be at 1.1, so that I can have maximum swing is equal to 1.8 minus ID is assumed to be 1 milliampere. So RD is for maximum swing possible for the output. So if you do this, is it actually 0.7 divided by 1 exponential minus 3? It's actually 700 ohm. So RD for maximum swing is 700 ohm. So the option is C. You may wonder, okay, what happens if the value of RD is 1K? The value of RD is 1K. Can you see, if you substitute this as 1K, can you see out of 1.8, 1 volt gone? So now how much you have? You left out with VD is equal to 0.8. So this will be at 0.8. So here they are at 0.8. So how much the swing you have? So you hardly have only 400 millivolt here, but almost 1 volt here. So here this is not symmetric. Here it is less, here you have more. So that's why a RD of 1K is not suitable to have a maximum swing, because you hardly have 400 mil, because you cannot go below this, because MOSFET will enter the linear region. Suppose if you take 900 ohm, if you take it as 900 ohm, so how much is this? Is it not 1.8 minus 0.9? Is it not, how much is that? 0.9 volt. So you are there at 0.9. If you are there at 0.9, you hardly have 0.5 here, and from here to here it is, here it is 0.9 means 0.9. So again it's not symmetric. So here you have 0.5, there you have 0.9. Suppose if you take 100 ohm, if you take 100 ohm, then this will be 1.8 minus 1 milli into 100 ohm, so which will become 1.7 volt. So now it is at this point. If it is at this point, this is 1.7. You hardly have 100 millivolt. Whether you have, now you have almost how much here? This is 1.3 volt. So this is 0.1 volt swing at the top side. At the bottom side, you have up to 1.3 volt. So neither of 1K, 900 ohm or 100 ohm will give maximum swing. when I say maximum swing, both both the positive and negative swing should be same, equal. So you have 0.7, if you have it as 700 ohm as the value of RD, that will give a 1.4 volt peak to peak swing of equal positive and negative halves, that is 0.7 plus 0.7. So the answer for this is 0.7, so this 0.7K or 700, here this is 700 ohm. Next, if the value of RD changes from 700 ohm to 1.3K, the MOSFET remains in saturation, remains in linear region, moves from saturation to linear region, don't know. So what is this? If the value of RD is changed from 700 ohm to 1.3 kilo ohm, what happens? Now let us see. Let us again go back to the same circuit. Now we know that if the value of RD is changed, this voltage will change. Suppose if the value of RD becomes, suppose here if the value of RD becomes 1.3 kilo ohm, so then what is this? Is it not, assuming a current of 1 milliampere, is it not 1.8 minus 1.3 volt? Is it not 0.5 volts? This is 0.5 volts is your VD. If the value of RD changes from, if RD changes from 1K to, from 700 ohm to 1.3K. When it is 700 ohm, what is the value of VD? It was 1.1 volt. This VD was 1.1 volt, 1.1 volt. Now when it is 1.3K, it was 0.5. It was 0.5. So does the value of VD, which is 1.1 and 0.5, will it keep the MOSFET in saturation region with this value of VGS? So VGS is 0.8, VTH is 0.4, the saturation voltage is VDS sat is equal to 0.4 volt. So when the value of RD is 700 ohm, VDS is 1.1 volt. When the value of RD is 1.3K, it is 0.5 volts. If you compare this 1.1 and 0.5, is it always more than 0.4? Since it is always more than 0.4, whether the value of RD is 700 ohm or 1.3 kilo ohm, MOSFET is in saturation region, because MOSFET will not go to linear region because VDS is certainly more than VDS sat. So the answer for this question is, if RD changes from 700 ohm to 1.3 kilo ohm, MOSFET remains in saturation region, So that's the answer. Hope it's clear. Thank you.